In the boundless cosmos, our solar system is not an entirely isolated island. It constantly exchanges matter and energy with the vast interstellar space. Among these exchanges, the most remarkable messengers are interstellar objects originating beyond our solar system. These celestial bodies, like cosmic drift bottles, carry the secrets of other stellar systems. It wasn't until 2017 that we first confirmed such a visitor, Oumuamua. Its arrival opened a new chapter in astronomy, making us realize interstellar objects are not theoretical fantasies but real entities. The subsequent appearance of Comet Borisov further confirmed this. It resembled a familiar solar system comet, only originating from a distant foreign land. However, the arrival of 3I Atlas completely changed the game. Thousands of times larger than Oumuamua, it proved more complex and enigmatic than Borisov. Its discovery wasn't the result of a meticulously planned sky survey. Instead, it was captured by human telescopes only after it had already penetrated deep into the inner solar system. The 3I in its name signifies it as the third confirmed interstellar object. Atlas bestows upon it the symbolic weight of a heavy burden, as if carrying the unknown knowledge of the cosmos. Its origins are deeply rooted in interstellar space. This implies it formed around a completely different star system. It may have been ejected by the gravitational forces of its parent star system billions of years ago. Thus began its long It traversed the vast, near-void expanse between stars, enduring cosmic conditions beyond our imagination. Ultimately, its trajectory intersected with our solar system. This convergence was extraordinarily fortuitous, given the vastness of interstellar space and the minuscule scale of Earth's target. The probability of it entering our solar system precisely at this moment and being discovered by us is minuscule. Is this pure luck or some unknown inevitability? This is the first mystery scientists seek to unravel. When we gaze at the night sky, those twinkling points of light seem eternal and unchanging. Yet interstellar visitors like 3I Atlas remind us that the universe is dynamic. Star systems do not exist in isolation. They are connected through these silent messengers. Studying 3I Atlas is not merely examining a celestial object. It is deciphering a precious sample from beyond our solar system. This sample may encapsulate the formation conditions and evolutionary history of its parent star system. Its scientific value is immeasurable. Its arrival offers us an unprecedented opportunity to directly study the constituent materials of an exoplanetary system, without waiting for distant starlight to traverse light-years to reach our telescopes. It is an exoplanetary specimen delivered right to our doorstep, awaiting our meticulous dissection and analysis. 3I Atlas first astonishes with its sheer scale. Preliminary observations estimate its diameter between 14 and 40 kilometers. For discussion purposes, scientists typically use its average value of approximately 25 kilometers. What does this size mean? It could easily cover a large city and its surrounding areas. Placed on Earth, it would be a truly formidable colossus. Among comets explored by humanity, it ranks as an absolutely massive celestial body. Its dimensions far exceed those of the two previous interstellar visitors. Oumuamua measured only a few hundred meters in length, while Borisov's comet nucleus had a diameter of about 1 kilometer. Compared to 3I Atlas, they appear minuscule. This immense size directly implies astonishing mass. Based on gravitational and 3I Atlas's mass could reach as high as 33 billion tons. This is a figure difficult to grasp intuitively. It equals dozens of times the total weight of all humans on Earth. It also equals the mass of a medium-sized mountain range. Such an immense mass traveling at high speed through space as a single entity is itself an extraordinarily remarkable phenomenon. Yet what truly sets 3I Atlas apart is not its colossal size, but its perplexing composition. Through ground-based telescopes and spectral analysis by the James Webb Space Telescope, scientists have gained insights into its surface chemistry. Traditional comets are often likened to dirty snowballs. with cores primarily composed of a mixture of water ice, dust, and rock. Water ice typically constitutes a significant portion of their mass, sometimes exceeding 50%. Yet 3I Atlas completely overturns this conventional understanding. Measurements of water molecule emission lines reveal an exceptionally low water content, accounting for only about 4% of its total mass. This stands in stark contrast to typical cometary composition, suggesting it resembles a dry asteroid rather than an ice-rich comet. Even more unusual is its anomalous metallic composition. Spectral analysis reveals strong nickel emission lines while iron content is relatively low. This reversal of nickel minus to minus iron ratios is extremely rare among natural celestial bodies. Within our solar system, known comets and asteroids typically contain far higher iron than nickel. This unique elemental ratio is more commonly found in human made industrial alloys, where nickel is valued for its superior corrosion resistance and mechanical strength. Of course, this does not conclusively prove it is artificial, but it at least indicates its formation environmental process differs fundamentally from familiar solar system bodies. Another key characteristic is its albedo, the surface's ability to reflect sunlight. Preliminary measurements suggest its surface is relatively dim, meaning it absorbs most sunlight. This may explain why it remains detectable even when far from the sun. However, whether its surface consists of rocky metals or complex organic matter still requires higher resolution observations to confirm. All these physical properties, size, mass, and anomalous composition, combine to paint a complex and contradictory picture. It exhibits both comet-like gaseous outgassing activity and asteroid-like rocky metallic characteristics. This hybrid nature is unprecedented within the solar system. It forces us to rethink the boundaries of celestial classification and seriously consider all possibilities, including those we once deemed impossible. 3I Atlas's orbit stands as the most direct evidence of its interstellar identity. When astronomers input countless observational data points into computers and perform retrospective and predictive calculations through complex orbital mechanics equations, a clear and definitive path emerges before our eyes, mathematically termed a hyperbolic orbit. This signifies that 3I Atlas possesses kinetic energy exceeding the solar system's escape velocity. It does not orbit the sun, but instead makes a brief deflection within the sun's gravitational field. Ultimately, it will depart the solar system forever, returning to interstellar space. Its orbital eccentricity is a staggering 6.137. This figure holds significance as it definitively distinguishes the solar system's temporary visitors from its permanent residents. Earth's orbital eccentricity approaches zero, indicating a near-perfect circle. Even comets from the distant Oort cloud typically have eccentricities around 1. Any value greater than 1 signifies a hyperbolic trajectory bound by the sun's gravitational pull. 3I Atlas's 6,137 eccentricity reveals an exceptionally open and high-speed orbit. The sun's gravity barely slowed it down, merely nudging its course, as if a hurried traveler merely passing through with no intention to linger. Its approach direction is equally coincidental, with its orbital plane forming a 175-degree angle to the ecliptic plane, the orbital plane of the solar system's planets. This is a nearly completely retrograde orbit, meaning it travels in the opposite direction to the planetary family, as if deliberately sneaking in through the back door to observe the entire system. Yet more remarkable is that despite its nearly perpendicular orbital plane, its path through the inner solar system precisely remains within 5 degrees above or below the ecliptic plane. This is no accident. The ecliptic plane is the dense zone of planetary matter where all the stories unfold. The probability of a randomly oriented interstellar object directly traversing this narrow region is extremely low, approximately only 0.%. This inevitably raises suspicion that its path was carefully chosen. Its timeline is equally thought-provoking. Upon reaching Perilhana, its closest approach to the Sun, it positioned itself precisely on the opposite side of the Sun relative to Earth. This placement rendered it invisible to ground-space telescopes at the time. It seemed to skillfully use the Sun as cover, concealing itself during the most critical moments. Subsequently, as it moved away from the Sun, it orchestrated a series of encounters. First, it made a close flyby of Mars at 29 million kilometers, then Venus. Next, on December 19th, it reached its closest point to Earth at approximately 216 million kilometers. Afterward, it would visit Jupiter. This sequence of planetary flyby windows was so perfectly timed, it seemed like a meticulously calculated reconnaissance route, designed to observe the major planets of the solar system from different angles. Each close encounter presented an exceptional observation opportunity, not only for us but for 3I Atlas itself. If it possesses any awareness or mission, these positions represent ideal data collection points. From a purely orbital mechanics perspective, this path is feasible, yet considering the vastness of interstellar space and the periodic nature of planetary orbits, the probability of such multiple coincidences occurring simultaneously is minuscule. It represents either an extremely fortunate statistical outlier or suggests some form of active control underlying its trajectory. NASA's Jet Propulsion Laboratory JPL Horizon system continuously updates its latest orbital calculations. Each new observation refines this trajectory further, while making its non-gravitational acceleration increasingly undeniable. These subtle yet persistent deviations from a purely gravitational path represent one of the deepest enigmas surrounding 3I Atlas. It tells us an unknown force is acting upon this object, pushing it to subtly alter its course. Whether this force stems from comet like natural outgassing or some form of propulsion system is currently the most intense and captivating debate in astronomy. Determining the rotation period of a distant celestial body is a meticulous exercise in scientific detective work. For interstellar visitors like 3I Atlas, we cannot directly image its surface features. Astronomers therefore employ a classic and effective method known as photometry. Its fundamental principle is straightforward. As a rotating object spins, the surface facing us constantly changes. If different regions of this object possess varying albedos, that is, their ability to reflect sunlight, then its overall brightness, as observed from Earth, will fluctuate periodically. When darker regions face us, it dims. When brighter regions face us, it brightens, by continuously unprecisely measuring its brightness over extended periods, recording these seemingly random fluctuations, and then employing powerful computer algorithms to uncover hidden periodic patterns, we can infer the object's complete rotation period. During the summer months of 2025, multiple independent astronomical teams worldwide deployed telescopes of varying sizes to collectively focus their gaze on 3I Atlas, continuously gathering its brightness data. These observational data are streamed into scientists' databases from across the globe. As researchers processed and analyzed this vast dataset, a crystal-clear signal emerged. All data pointed to the same period, 16 hours and 16 minutes, with an extremely narrow margin of error of 0.1 hours. In astronomical measurement, this precision rivals laboratory standards. Multiple teams using different instruments on separate nights independently arrived at identical results. This significantly enhances the reliability and persuasiveness of the discovery. The rotation period itself presents a fascinating data point. It differs from both rapidly spinning asteroids, which complete revolutions in minutes or hours, and tidally locked bodies, which perpetually face their primary star with the same side. 16 hours and 16 minutes roughly equates to 2-3 of an Earth day. This intermediate value is uncommon among solar system bodies. It appears so deliberate, as if a carefully considered choice. Photometric data not only reveals the period, but may also conceal clues about the object's shape. The specific form of the light curve can indicate whether the body is nearly spherical or highly elongated. Preliminary analysis indicates Atlas 3I exhibits relatively smooth brightness variations, suggesting it may be a relatively regular sphere rather than an extremely elongated cigar shape. This stands in stark contrast to the previously discovered Oumuamua. The elegance of this measurement method lies in its avoidance of costly space missions. Through patient ground-based and near-Earth orbit telescope observations alone, we have unlocked a fundamental physical parameter of this celestial body billions of kilometers away. The 16.16- rotation period became the cornerstone of our understanding of 3I Atlas, and starting point for all subsequent anomalies and speculations. Upon learning that 3I Atlas possesses a 16.16- rotation period, the next question naturally arises: what does such a rotation speed mean for the object itself? To grasp this, we need to perform some simple physics calculations. Imagine standing on the equatorial surface of this roughly 25-kilometer diameter object. You slowly rotate along with it. Due to its long period, the tangential speed at its surface is actually very slow, between approximately 0.25 and 0.5 meters per second. This equates to human walking or jogging speeds. From a physical perspective, it would cause almost no discomfort. You might not even feel noticeable centrifugal force. Yet for the celestial body itself, even such a slow rotation is critically important. This is especially true for objects like comets, which are typically considered loosely aggregated bodies. They are not composed of solid rock in a single piece. Instead, they rely more on their own weak gravitational pull and the cohesive force of ice to hold them together, much like a loose snowball made of sand and snow. If the rotational speed becomes too fast, the resulting centrifugal force could exceed the weak gravitational pull, causing the entire structure to disintegrate as material is flung into space. This is known in astronomy as the rotational breakup threshold. For a body with typical comet density about 0.5 grams per cubic centimeter, the critical rotation period is usually around several hours. Yet 3I Atlas's 16.16- hour cycle falls well below this dangerous threshold. Its rotation can be described as leisurely unsafe. This falls entirely within the expected range of natural celestial behavior. This appears to be an argument supporting its natural origin. Another key parameter is escape velocity, the minimum speed an object requires to completely break free from 3I Atlas's gravitational pull. Calculations indicate this velocity is approximately 10 meters per second. Comparing this to the maximum and possible equatorial rotation speed of 2.5 meters per second reveals that surface material would need to gain 4 times the energy of its current rotational speed to be flung into space. Its gravity firmly controls its own material, with no signs of disintegration due to rotation. From a purely physical stability perspective, 3I Atlas's rotational state is perfectly balanced. It rotates slowly enough to avoid self-destruction, yet fast enough to provide dynamic stability. All this appears so reasonable, as if it were a natural celestial body that has tumbled through space for billions of years, gradually sculpted by gravity and tidily adjusted into its present stable state. This rotational speed is so ordinary, it should not have raised any suspicions, until we juxtaposed it with another observed fact: the jets that refuse to align with its spin. It is precisely this sharp contradiction between seemingly normal rotation and highly anomalous gas behavior that elevates the entire puzzle to a new level. When natural explanations falter, scientific inquiry demands we broaden our horizons to consider all logically plausible possibilities. Among these, the most destructive is the artificial gravity hypothesis. This theory proposes that 3I Atlas's 16.16- rotation period is not a natural outcome, but a deliberately engineered choice, designed to create an artificial gravity environment for its potential internal occupants or equipment. Prolonged exposure to microgravity proves profoundly detrimental to living organisms, whether humans or other life forms. We hypothesize all face a cascade of issues: bone loss, muscle atrophy, cardiovascular dysfunction, and more. For an interstellar voyage potentially spanning millennia or even millions of years, resolving the gravity issue is a prerequisite for survival. Currently, the only viable long-term solution known to human physics is generating centrifugal force through rotation. Imagine a rotating space station where centrifugal force pushes objects outward to simulate gravity along the station's inner walls. This is known as artificial gravity. However, selecting the rotation speed is not arbitrary. It requires a delicate balance. Rotating too fast induces a strong Coriolis effect, causing significant gravitational disparity between the head and feet, and triggering severe dizziness and nausea. Based on decades of research from manned spaceflight and ground simulations, the comfortable upper limit of rotation for humans is approximately 6 revolutions per minute. Converted to orbital periods, this equates to over 10 minutes per revolution. The 3I Atlas's 16.16- our orbital period falls far below this threshold, so slow that the Coriolis effect becomes virtually negligible. At this speed, organisms can move freely without discomfort. From a comfort perspective, this is nearly an ideal choice. Next, let's calculate the artificial gravity achievable at this rotation speed and source. On its equatorial surface, using the centrifugal force formula, an equatorial object with a 25-kilometer diameter and 16-r period generates only about 0.4% of Earth's gravity. This value is far insufficient for maintaining human physiological health and is only marginally better than complete weightlessness. But here lies a crucial shift in perspective. Why assume the occupants are human or require Earth- standard gravity if the occupants are extraterrestrial life forms from a low-gravity world? Say a planet with surface gravity only a fraction of Earth's, then a 0.4G environment might be entirely sufficient for them. It could maintain normal fluid distribution and provide basic skeletal-muscular noggin to avoid the worst effects of microgravity. Another possibility is that their living quarters aren't located on the equatorial surface, but within internal structures closer to the rotational axis, within a massive rotating cylinder. Artificial gravity levels vary at different radii, with gravity diminishing toward the center and becoming zero along the central axis. This design enables creating distinct gravity zones within the same facility, such as deploying high-gravity industrial facilities at the periphery, while locating living quarters closer to the center. This embodies the core concept of classic space habitat designs like the Stanford Torus. Furthermore, rotation offers another crucial benefit: gyroscopic stability. A massive object spinning rapidly around a fixed axis possesses immense angular momentum. It strongly resists any force attempting to alter its rotational direction. This provides unparalleled navigational stability for interstellar voyages during light-year journeys. Even a minute deviation in course, amplified over vast distances, could result in missing the target by millions of kilometers. Rotation acts as a natural gyroscope, locking the spacecraft onto its predetermined course and resisting external disturbances like interstellar medium. Finally, this rotational cycle perfectly aligns with the observed directional jet streams. If the 3I Atlas were a controlled spacecraft, it would require course corrections and attitude control while rotating. The 16-hour rotation cycle provides ample window time for precise ignition of propulsion systems at specific rotational phases to generate net thrust in a spatially fixed direction. This perfectly explains why the jets consistently point in the same direction, regardless of the core's rotation. They are not passive venting but actively controlled thrusters, whose ignition timing is meticulously calculated to compensate for the body's rotation. In summary, the 16.16-hour rotation cycle achieves a near-perfect engineering equilibrium between the comfort of artificial gravity, gyroscopic stability, and propulsion control flexibility. It appears less like a naturally occurring random number and more like a deliberately optimized design specification. When the 3I Atlas's imaging data arrived from telescopes worldwide, what astonished astronomers most was not the nucleus itself, but the enormous bizarre jets extending from it. These jets differed entirely from any structure previously observed on comets. They were not diffuse, fuzzy halos of fan-shaped dust tails, but instead exhibit an astonishing sharpness and straightness, as if invisible cosmic rulers had drawn perfect lines. Astronomers employ a specialized term to describe this characteristic collimation. Collimation means the ejected material streams maintain a high degree of parallelism, with minimal dispersion during propagation. A common terrestrial example of collimation is a laser pointer beam. which traverses great distances while maintaining nearly constant spot size. In contrast, a flashlight beam rapidly diverges and widens. The jets from 3I Atlas exhibit precisely this laser-like high collimation. Observational images clearly trace the sharp edges of these jets, whose width remains virtually unchanged, over distances spanning hundreds of thousands to even 1,000,000 kilometers. What does 1,000,000? It's nearly 3 times the distance from Earth to the Moon. Imagine a perfectly straight beam stretching 3 times farther than Earth to the Moon, yet only thousands of kilometers wide. This implies a divergence angle less than 0.2 degrees. Such extreme collimation is unheard of in natural cometary activity. Typically, after leaving the nuclear surface, cometary jets rapidly expand into a bell-shaped cone due to molecular collisions, solar radiation pressure, and magnetic fields, rapidly expanding into a funnel-shaped cone. After traveling thousands of kilometers, they become indistinct. The jets of 3I Atlas defy this physical intuition. They appear constrained by some invisible force, compelling them to follow a predetermined straight path. Another key anomaly is the multidirectionality of these jets. They are not solely ejected toward the Sun. Observations clearly capture at least 3 distinct jet types. One is the expected solar-facing jet, where material flows toward the Sun. Another is the highly anomalous anti-solar jet, where material flows away from the Sun. A third is the lateral jet, oriented roughly perpendicular to the Sun. This multidirectionality completely shatters many simple natural explanation models, since cometary jets are fundamentally the result of solar-driven ice sublimation. Their power source is the Sun's heat. Therefore, natural outflows should primarily occur on the sunlit side, and from a dust tail pointing away from the Sun under the influence of Earth's air pressure. The persistent anti-solar outflow is physically difficult to understand. It implies that material is moving toward the Sun against radiation pressure, or that there exists an independent source of material not driven by sunlight. All these characteristics combined paint an extremely bizarre and discordant picture: a slowly rotating nucleus, extending multiple streams across vast interstellar distances, yet maintaining razor-sharp fixed orientations, pointing in distinct directions as if executing independent missions. This highly ordered and precise geometric structure stands in starkest contrast to the chaotic, random cometary activity we observe in nature. The most fundamental contradiction within 3I Atlas lies in the irreconcilable physical conflict between its rotating nucleus and the fixed direction of its jets. This is a simple problem of geometry and kinematics. Let us illustrate with an earthly analogy. Imagine a rotating garden sprinkler on a lawn. As the sprinkler rotates, its water jets do not shoot straight in a fixed direction. Instead, it traces an arc in the air, forming a spiral pattern of water droplets. This water trail directly mirrors the sprinkler's rotational motion. Now apply this principle to 3I Atlas. Its nucleus completes one rotation every 16.1 hours. If the jets on its surface were passively ejected by geological features like natural vents, their direction would constantly shift with the nucleus's rotation. During one full rotation of the nucleus, the jet direction sweeps through 360 degrees. Now consider the time required for material ejected from the vent to travel 1,000,000 kilometers. Calculating at a typical cometary ejection velocity of 400 meters per second. This journey takes approximately 20-9 days. Over these 20-9 days, the nucleus of 3I Atlas completes roughly 40-5 full rotations. 40-5 rotations. This implies that the first ejected clump of material and the last ejected clump of material experience a difference of 40-5 cycles in the direction of the outflow relative to the outflow orifice. If the outflow were continuous, this rotational effect should cause the outflow to coil in space into an extremely complex corkscrew-like structure, or at the very least, due to material being ejected successively from different directions, it should blend into a broad, diffuse fan-shaped pattern. In any case, we should not observe sharp beam stretching millions of kilometers yet pointing straight toward a fixed direction. Yet the observational images ambiguously reveal these jets do precisely that. They refuse to follow the rotation's dictates. They point like searchlights toward a fixed coordinate in the cosmos, as if the rotation of the nucleus beneath them is entirely irrelevant. Scientists have, of course, considered a natural possibility: pulsed ejection. Perhaps deep valleys or fissures exist on the core surface, illuminated only when it rotates to specific angles, briefly activating ice sublimation to produce a jet, which repeats when the same location is illuminated again in the next rotation cycle. This would create a series of discrete material clumps in space, rather than a continuous jet, but calculations indicate this mechanism should produce a series of discrete gas clouds spaced roughly 23,000 kilometers apart, rather than the continuous, smooth plume we observe. More critically, the pulse model fails to explain the existence of anti-solar jets. How could a deep valley dependent on solar illumination produce intense jets when facing away from the sun? This fundamentally violates the law of energy conservation. The rotating core and the stationary jets constitute the deepest paradox of 3I Atlas. It compels us to seek an independent control mechanism. Faced with the rotation paradox, the scientific community must systematically evaluate all possible explanations. First, we examine natural possibilities. One hypothesis involves magnetic collimation. In certain astrophysical environments, such as the jets of young stars or black holes, powerful magnetic fields can constrain streams of charged particles, maintaining high collimation over vast distances. However, comets are typically frozen mixtures of rock and dust. They lack an internal liquid metal core capable of generating strong magnetic fields. Their intrinsic magnetic fields are extremely weak, insufficient to produce magnetic confinement, capable of controlling jet structures. Achieving magnetic confinement would require a powerful artificial magnetic field source. This alone points toward technological possibilities. Another natural explanation involves surface features resembling physical nozzles, such as elongated canyons or channels, which naturally constrain the direction of gas expansion. Yet on a natural body subjected to billions of years of space weathering, it is difficult to envision the formation and preservation of such perfectly aligned, multi-directional channel structures. More critically, even if such structures existed, they would rotate with the nucleus, failing to explain the jet's fixed orientation. Furthermore, the mass loss rate is severely mismatched with the thrust required for the observed non-gravitational acceleration. To generate thrust of that magnitude through passive sublimation would require losing 13% of the total mass, over 43 billion tons of material. This should result in the nucleus being enveloped by a massive dust and gas cloud, yet the actual observed coma is relatively mild. Now let us turn to the artificially controlled hypothesis. This hypothesis proposes that what we observe is not passive outgassing, but an active, directional propulsion system in operation. These jets are essentially spacecraft thrusters. They are mounted on balancing rings capable of compensating for the core's rotation, or their ignition timing is precisely calculated to operate only in pulses when the nozzle rotates to a specific orientation, thereby achieving a net, fixed thrust direction in space. This principle is fundamentally consistent with how modern satellites use reaction control thrusters for attitude adjustment, only scaled up by countless orders of magnitude. Under this model, the jet's extremely high collimation becomes entirely logical, because they are ejected from meticulously engineered nozzles, much like rocket engine nozzles that control exhaust expansion through geometry to maximize thrust and efficiency. Multidirectionality is also perfectly explained. Sun-facing, anti-solar, and lateral jets together from a complete 3-axis attitude control system. By activating these thrusters in different combinations and sequences, the spacecraft can precisely adjust its orbit and orientation, while maintaining rotation to provide artificial gravity and stability. The propulsion hypothesis also resolves the paradox of mass loss versus thrust mismatch. A spacecraft utilizing internal energy sources like nuclear fusion or more advanced propulsion systems derives its thrust primarily from the ejection of highly efficient propellants it carries. Rather than sacrificing its own structural mass through evaporation, the small amount of water or other molecules it expels may be intentionally released merely to mimic cometary activity. Its true thrust far exceeds the momentum these volatiles could provide. When examining these two opposing explanations, the naturalistic interpretation faces one insurmountable obstacle after another. It requires invoking a series of extremely specific and coincidental conditions. Each condition individually has a low probability. When all must occur simultaneously, their combined probability becomes minuscule. The artificially controlled explanation, though startling at first hearing, offers a unified and concise framework to simultaneously account for multiple independent anomalies: collimation, multidirectionality, directional stability, and thrust variations. Under the scientific principle of Occam's razor, the explanation requiring the fewest ad hoc assumptions often approaches the truth. The jet from 3I Atlas strongly suggests that what we observe may not be geological activity, but rather manifestations of technological activity. Science's initial response is always to explain new phenomena through known natural processes. For 3I Atlas, astronomers first constructed various natural models, yet these models all face severe challenges when confronted with observational data. The primary natural explanation proposed is an extremely active outgassing model. This model posits that 3I Atlas may be composed of some unknown, super-minus volatile substance. When heated, this material could generate exceptionally powerful jets, thereby explaining the observed non-gravitational acceleration. However, this model immediately encounters a composition mismatch problem. Spectral measurements reveal insufficient quantities of new material. Its abundances of water, carbon dioxide, and carbon monoxide are all too low, unable to account for the massive mass loss required by the model. More critically, such intense outgassing activity should rapidly erode the nucleus's surface or even cause structural fractures. Yet observations show 3I Atlas remains intact, showing no signs of large scale disintegration or dramatic surface changes. The second natural model seriously considered is the pulsed illumination hypothesis. This model attempts to explain the fixed direction of the jets. It posits the existence of extremely steep valleys or cavities on the surface of the nucleus. These structures would only become active during a brief window when precisely aligned with the sun. During this alignment, the valley bottoms would be exposed to sunlight, instantly sublimating and generating jets. The jets would cease during the remainder of the rotation cycle. This would result in the formation of discrete clumps of material in space, rather than a continuous jet. However, observations reveal a smooth, continuous ejection structure. More critically, this model fails entirely to explain the existence of anti-solar jets. How could a sunlit deep valley generate jets when facing away from the sun? This violates the fundamental law of energy conservation. The third natural explanation is the magnetic field collimation hypothesis. In certain astrophysical environments, such as young stars, powerful magnetic fields can constrain plasma flows into collimated jets. Perhaps 3I Atlas possesses an exceptionally strong endogenous magnetic field, capable of guiding charged particle streams to remain perfectly straight. However, comets are frozen mixtures of rock and dust. They lack the liquid metallic cores found in planets that generate electricity to produce strong magnetic fields. Non-cometary magnetic fields are so weak they can be considered negligible. To generate a magnetic field powerful enough to control jets spanning millions of kilometers would require an extremely potent artificial magnetic source. This alone shifts the question toward technical feasibility. The fourth natural model is the fragment trajectory hypothesis. This model proposes that 3I Atlas fractured near Pearl Harbor. Larger ejected fragments traveled along ballistic trajectories, forming the linear structure we observe from Earth. This would make the jet direction independent of the nucleus's rotation. However, subsequent high-resolution observations clearly show that the nucleus of 3I Atlas remains intact as a single coherent object. No signs of large fragments were detected in its vicinity. If a massive fragmentation capable of producing those jets had occurred, we should now observe a distinct debris cloud. Yet this is not the case. A fifth possible natural explanation involves unknown comet physics. Perhaps 3I Atlas simply exhibits comet behavior we have yet to comprehend. After all, we have studied only a limited number of solar system comets in detail. While interstellar objects may originate from entirely different formation environments, they follow different physical laws. This explanation is philosophically valid, but it effectively amounts to admitting our current comet physics is incomplete. More importantly, it must simultaneously explain over a dozen distinct anomalies. Each requires a special unknown mechanism. The common dilemma facing these naturalistic models is ad hoc nature, specifically, the need to invent a unique explanation for each anomaly. Moreover, these explanations are often mutually incompatible. For instance, models explaining anomalous constituents cannot account for jet collimation. Models explaining jet collimation cannot account for non-gravitational acceleration. Models explaining non-gravitational acceleration cannot account for anti-solar jets. This practice of continuously layering ad hoc assumptions renders naturalistic explanations increasingly cumbersome and inelegant in scientific terms. The issue becomes even more apparent from a probabilistic perspective. Suppose the prior probability of explaining each major anomaly through natural processes is 2%. When 12 such anomalies coexist on a single object, the combined probability of them all being natural coincidences becomes an extremely small number, 1 in a billion or even lower. Though the universe is vast enough for a 1 in a billion event to occur, when we actually encounter such an occurrence, we have a responsibility to seriously consider other possibilities, including one that could provide a unified explanation for all anomalies. The fundamental limitation of natural explanations lies in their attempt to interpret phenomena potentially beyond our current knowledge, using physics we already understand. Science should indeed prioritize natural explanations, but when natural explanations require continually introducing new ad hoc hypotheses that themselves cannot be independently verified, we must have the courage to expand our hypothesis space and consider possibilities that initially seem extraordinary. This is not abandoning the scientific method. It is precisely the scientific method that demands we adjust our assessment of different hypotheses' credibility. Adjust credibility assessments for different hypotheses based on the weight of evidence. For the 3I Atlas, natural explanations continue to struggle to find a way out, yet every path appears exceptionally narrow and fraught with obstacles. This has transformed what was once deemed an inconceivable alternative explanation, the artificial origin hypothesis, from a wild conjecture into a scientific hypothesis that must be taken seriously, in stark contrast to the natural explanation's laborious progress. The artificial origin hypothesis demonstrates formidable explanatory power. It unifies numerous isolated anomalies on the 3I Atlas into a coherent whole through a single core mechanism, a propulsion system under intelligent control. The first and most robust evidence stems from its precise orbital characteristics. Orbital solution data from JPL's HiRISE system indicates that 3I Atlas's orbit requires non-gravitational acceleration parameters to perfectly fit observational data. These parameters represent minute, yet persistent thrust forces acting upon the object. When substituting these parameters into equations to calculate their actual force output, an irreconcilable contradiction emerges. To generate such immense thrust, if achieved solely through Comet's typical sublimation jet mechanism, it would require shedding approximately 13% of its total mass. This equates to over 43 billion tons of ice and dust being ejected into space. Such massive mass loss would form an exceptionally bright and vast coma around the nucleus. Its scale should be large enough to be clearly visible through amateur telescopes. It would also likely cause the nucleus to disintegrate due to excessive mass loss. However, the actual mass loss rate measured by spectral observations is nearly 1,000 times lower than this theoretical requirement. The coma remains relatively faint, and the nucleus retains its structural integrity. This contradiction points to a conclusion. The source of thrust is not passive mass ejection, but rather an efficient, internally energy-driven propulsion system. Such a system generates thrust using specific propellants, rather than relying on the evaporation of its own structural mass for recoil. The second key piece of evidence is the anomalous behavior of the jet's into-rotation paradox, which we explored in detail in the previous chapter. These jets maintain high collimation and fixed direction while ignoring the nucleus's rotation. From an engineering perspective, this perfectly aligns with the model of a rotating spacecraft using directional thrusters for attitude control. The thrusters are fixed to the hull and rotate with it, but their firing timing is precisely calculated. They operate only in brief pulses when the spacecraft rotates to specific phases. This generates a net, directionally fixed thrust in space. It is analogous to a spinning figure skater, who can control their rotational speed by extending and retracting their arms at precise moments during the spin. This represents an active control mechanism requiring exact timing. The third piece of evidence concerns the geometric properties of its trajectory and the potential reconnaissance logic. 3I Atlas entered nearly perpendicular to the ecliptic plane, yet precisely traversed the orbital plane of the planets. This alone represents a low-minus probability event. Even more unusual is the timing of its perilhana, allowing it to cleverly hide behind the Sun during its closest approach, evading Earth's observation. Subsequently, it approached Mars, Venus, and Earth in turn at optimal observation distances. The sequential occurrence of this series of coincidences carries an extremely low combined probability. If interpreted as a planned flyby mission, this trajectory appears exceptionally efficient and rational. It maximizes opportunities for close-range observation of multiple inner solar system planets. The fourth piece of evidence is its remarkable internal consistency. The artificial origin hypothesis provides a framework capable of unifying its anomalous composition, structure, and dynamics. For instance, its unusual nickel-iron ratio and low water content can be explained by the use of durable alloy materials in spacecraft construction, rather than natural ice-rock mixtures. Its stable brightness evolution, unaffected by drastic variations in solar distance, aligns with characteristics of internal energy drive, rather than passive solar heating. Its extreme polarization signals may reflect a highly ordered engineered surface, rather than randomly distributed natural dust. These features are no longer 12 isolated puzzles, but 12 distinct facets of a single puzzle, collectively pointing to a designed and constructed object, rather than a naturally formed celestial body. The fifth compelling piece of evidence concerns its potential camouflage strategy. If an extraterrestrial probe sought to traverse the solar system for reconnaissance, while avoiding immediate excessive suspicion from indigenous civilizations, namely us, disguising itself as a common natural object, a comet, would undoubtedly be the optimal strategy. It would deliberately release water vapor and dust to create the illusion of a coma and tail, making it indistinguishable from a comet under cursory observation. Yet under more precise measurements, traces of its control systems, such as unobscured jets, and structural characteristics, such as anomalous composition, would be revealed. This flawed disguise may precisely be the cleverest evidence of its artificial origin. It is sufficient to generate scientific disagreement and debate, thereby buying time for its mission to complete, without immediately triggering global panic or reaction. Finally, an argument from Bayesian probability. When confronted with multiple independent, low-probability anomalies, scientifically we calculate the combined probability of their simultaneous occurrence for the 12 major anomalies in the 3I Atlas, even if each individual occurrence is set at a 1% probability. The natural probability of all appearing on the same object would be an extremely low value in the trillions minus to minus 1 range. While not entirely impossible, such an improbable event compels us to seriously consider the non-natural explanation that could link these anomalies together. The artificial origin hypothesis, though initially appearing as an extraordinary claim, points to a conclusion, may well be the least extraordinary way to explain this extraordinary evidence. The accumulation of these chains of evidence does not point to a 100% certain conclusion. Rather, like pieces of a puzzle, they gradually push the image toward a direction once deemed inconceivable. This demands we approach this potential interstellar visitor, one that may be rewriting human history, with open-mindedness and rigorous scrutiny. Faced with the numerous anomalies of the 3I Atlas, the scientific community requires a rigorous evaluation framework that transcends qualitative debates. This is precisely where probabilistic assessment and the scientific method play a crucial role. We cannot rely solely on intuition to judge whether it is man-made. We must employ systematic and quantitative analysis. In science, we often use Bayes' theorem to update our belief in a hypothesis, continuously adjusting the likelihood of an event as new evidence emerges. For the 3I Atlas, our prior probability might be low. After all, every suspected extraterrestrial signal in history has ultimately proven natural, but with each piece of anomalous evidence, this probability is constantly recalculated. Imagine a balanced scale. Initially, the scales heavily favor the natural origin side. Each new piece of evidence adds weight to the artificial origin side. At first, a few weights might be light, causing only a slight tilt. But when 12 independent, anomalous pieces of evidence are placed on one side simultaneously, the scales begin to tilt significantly. The crucial question is whether these pieces of evidence are truly independent. If the nickel-iron anomaly and the anti-solar jet stem from the same fundamental cause, they should not be counted repeatedly. Scientists are working diligently to untangle these connections, but even applying the most generous discount for correlation, the combined probability of the remaining evidence remains disturbingly low. The scientific method requires us to propose falsifiable hypotheses. The artificial origin hypothesis is equally falsifiable. If we discover the jets actually bend with rotation, or their composition ultimately proves to be known minerals, this hypothesis would be disproven. It is precisely this falsifiability that makes it a scientific hypothesis, rather than metaphysics. Current evidence supporting artificial origin is entirely circumstantial. We have not detected radio signals from it, nor captured clear images of artificial structures. This leads many scientists to remain cautious. They rightly point out that extraordinary claims require extraordinary evidence. Yet we must also guard against another bias, the inertia of excessive conservatism. Scientific history is replete with concepts initially dismissed as absurd yet later proven true. Plate tectonics and the Big Bang Theory were both once considered heretical. The key lies in whether the quality and quantity of evidence are sufficient to drive a paradigm shift, to evaluate such discoveries more objectively. Astronomer Rivi Loeb proposed a 1 to -10 assessment scale, known as the Loeb scale, to quantify the likelihood that a celestial object exhibits technological features. The MUA scored around 4, indicating intriguing but inconclusive evidence. 3I Atlas also falls within a similar score range based on current evidence. The value of the scale lies in its allowance for intermediate states. We can state that an object has a 30% or 40% probability of being artificial, without getting bogged down in binary yes minus or minus no debates. This probabilistic mindset aligns more closely with the essence of science. To 3I Atlas, the probability assessment isn't about arriving at a definitive answer, but guiding our next steps. If the probability of artificial origin is only 1 in 1,000, then routine observation may suffice. But if that probability rises to 10% or even 30%, it warrants mobilizing additional telescope resources. For deeper analysis, all current analysis relies on remote observation. The most decisive evidence may require close range detection. Regrettably, no spacecraft can reach 3I Atlas in time. This means that in the foreseeable future, we may never obtain a 100% certain answer. This raises a profound question in the philosophy of science. When definitive experiments are impossible, how do we make the best judgments amid uncertainty? Here, probability assessment becomes our most reliable compass. It guides us based on existing knowledge, toward which possibilities warrant serious consideration. The essence of scientific exploration is navigating the ocean of uncertainty. We chart the most probable map using available data, while remaining ready to adjust our course with new discoveries. For 3i Atlas, this map increasingly points toward a stunning possibility. Ultimately, science is not about certainty, but about making the most reasonable inferences based on evidence. With each new observation, our probabilistic assessment of the true nature of the 3i Atlas continually evolves. This process itself embodies the purest expression of science. Throughout the entire observational history of 3i Atlas, the most anticipated and controversial dataset undoubtedly comes from the HiRISE camera aboard the Mars Reconnaissance Orbiter. This powerful camera successfully captured images of 3i Atlas in early October 2025, when it flew past Mars at a distance of approximately 29 million kilometers. The timing and location of this observation held unparalleled scientific value. At that time, 3i Atlas had recently passed its perihelion, and its activity level remained at its peak, with the plume exhibiting its most dynamic and complex behavior. From Mars' perspective, the geometric relationship between Earth, 3i Atlas, and the Sun provided a perfect side view, enabling us to observe those perplexing features from an entirely new angle, particularly the mysterious anti-solar pointing structure. HiRISE's resolution is its most formidable asset. It is designed to resolve objects as small as a desk on the Martian surface. From an orbital altitude of 300 kilometers, although 3i Atlas was much farther away, HiRISE still achieved a spatial resolution of approximately 30 kilometers per pixel. This may not sound particularly fine, but considering the target's distance and size, it is a full 3 times the resolution of the Hubble Space Telescope. This represents an unprecedented vantage point. These images can answer several key scientific questions. First, the true shape and structure of the nuclear body itself. Ground-based observations reveal only a fuzzy point of light. HiRISE images may reveal whether it exhibits regular geometric shapes, whether it has distinct edges or flat surfaces. Such features could suggest engineered design, rather than a naturally formed irregular appearance. Second, patterns of surface albedo variation. Natural bodies typically show randomly distributed light and dark areas. Artificial objects may exhibit more regular patterns, such as symmetrical markings or functionally designated zones. Even subtle regularities in albedo could provide crucial clues to technical features. Third, the origin and spatial distribution of the jets. HiRISE images can precisely show from which specific locations on the core the jets are emitted. Are these locations randomly scattered or arranged in some ordered array, a jets emanating from discrete individual outlets or from extended linear structures? This information is crucial for distinguishing natural outgassing from engineered propulsion systems. Fourth is the true nature of the solar-facing structure. Observing this sun-pointing feature from Earth has long been controversial, as it could merely be an illusion caused by perspective effects. HiRISE's oblique viewing angle can resolve this question once and for all. If it is indeed physically oriented toward the Sun, it would pose a significant challenge to existing comet physics. Fifth concerns the environment surrounding the nucleus. Images may reveal the presence of undiscovered fragments or companion bodies, details potentially missed by ground-based observations. These are crucial for assessing whether the object has undergone fragmentation or is a composite structure. From an engineering perspective, these images hold additional value. If 3i Atlas is indeed a spacecraft, HiRISE's resolution may suffice to identify macroscopic structural features, such as radiator-like grid structures, asymmetric protrusions, or devices resembling communication antennas. even if such obvious technological features remain unseen. Surface material uniformity, or anomalous geometric symmetry, could serve as indirect evidence supporting artificial origin. The data volume of these images is immense. Each pixel contains information about composition, temperature, and physical state. Through advanced spectral analysis and morphometic techniques, scientists can extract information far beyond ordinary visual inspection, such as surface thermal properties, albedo variations across different regions, or even the detection of anomalous hotspots, all potentially indicating the presence of internal energy sources rather than reliance solely on solar power. In scientific methodology, HiRISE imagery provides a rare objective reference point. Prior debates regarding the 3I Atlas were largely based on circumstantial evidence and theoretical inferences. These images provide direct morphological evidence. They are quantifiable, repeatable analyses, hard data unaffected by atmospheric disturbances. Global research teams can independently analyze the same image set, reaching their own conclusions. This transparency and reproducibility lie at the core of the scientific process. Yet these potential scientific values remain unrealized precisely because image release is delayed. Every day of delayed wastes these unique observational opportunities. Because 3I Atlas is rapidly moving away from its captured state, we are losing the ability to precisely compare HiRISE's instantaneous snapshot with subsequent observations. Understanding the nature of 3I Atlas may well depend on these locked -away pixels. They could validate our boldest hypotheses, or lead us to entirely new, unknown natural phenomena. Regardless, their scientific value is immeasurable. These scientifically invaluable HiRISE images remain partially withheld from public release since their completion in early October 2025. This delay stems not from technical processing difficulties, but from entanglement in bureaucratic procedures. The immediate cause is the U.S. federal government shutdown, during which NASA is classified as a non-essential agency. Its public outreach and press release activities were severely restricted due to 3I Atlas's interstellar nature and the widespread attention it generated. These images were officially flagged as data possessing significant news value. Under the regulations during the shutdown, such data could not be released until government operations resumed. This classification itself is quite intriguing. The Mars Reconnaissance Orbiter transmits a vast amount of Martian surface imagery daily, and this data continues to be publicly released. Only the 3I Atlas images received special treatment. The official explanation is that the discovery of an interstellar object constitutes major scientific news, and thus requires adherence to stricter release protocols. However, this selective secrecy has sparked widespread concern within the scientific community. A deeper issue lies in the decision-making mechanism for data release. When scientific discoveries may have profound implications, which institutions or individuals hold the authority to determine the timing of data disclosure? If these images indeed reveal non-natural features, should scientists and the public be informed immediately, or must they undergo some internal evaluation process? This delay inflicts substantial harm on scientific research. 3I Atlas is a rapidly evolving dynamic system. Its jet structures and surface activity change daily. Images captured in October now show significant divergence from current conditions. We have thus lost a golden opportunity for time-series comparative studies. Precise tracking of how its surface activity varies with distance from the Sun is now impossible. More critically, this delay undermines the spirit of scientific collaboration. Astronomy has historically thrived on open cooperation. Data sharing enables global researchers to pool their insights and collectively advance the frontiers of knowledge. When critical data is locked away, it not only hinders scientific progress, but also erodes public trust in research institutions. During the same time frame, China's Tianwen probe team also acquired image data of 3I Atlas, though at lower resolution. They chose to share it immediately. This openness stands in stark contrast to NASA's conservatism. In the quest to explore the unknown, transparency and collaboration should take precedence over bureaucratic procedures. Despite the setback of data delays, the scientific community is actively preparing for the close flyby on December 19, which will be a decisive moment for studying 3I Atlas. The global observation network is now on high alert, from Hawaii's Keck telescope to Chile's Very Large Telescope. All major ground-based observatories have allocated dedicated observation time. The Hubble and James Webb Space Telescopes have also established intensive observation plans. Leveraging their unique orbital positions, they will bypass atmospheric interference to capture the sharpest possible images. The scientific objectives for this approach are clear. First, through high-resolution spectral analysis, to precisely determine its molecular composition in the surface and coma, with particular focus on anomalous ratios detected in prior observations, such as nickel-iron ratios and cyanide abundances. Isotopic measurements will provide the chemical fingerprint of its progenitor galaxy. Second, detailed dynamical studies of the jets. Through continuous high-speed imaging, scientists aim to capture Pulsian patterns of the jets and their phased relationship with the central object's rotation. Doppler measurements will reveal precise velocities of jet material to determine whether it conforms to thermal sublimation models or exhibits unnatural acceleration characteristics. Radar observations will serve as another critical tool. Though the HiRISE Observatory is no longer operational, joint observations from Goldstone and Green Bank may still yield valuable echo data, enabling precise determination of the nucleus's shape, size, and surface roughness, and may even probe its internal density distribution. The amateur astronomy community also plays a vital role. Global enthusiasts form a distributed observation network whose strength lies in providing near-continuous monitoring to bridge gaps between professional telescope observations. Many significant astronomical discoveries stem from such collaboration between professional and amateur sectors. Perhaps the most anticipated are unexpected discoveries. If 3I Atlas indeed has artificial origins, close-range observation may reveal previously unnoticed details, such as geometric patterns on its surface, anomalous thermal distributions, or even the detection of unnatural electromagnetic radiation. Yet we must maintain rational expectations. Even the most advanced observational equipment may fail to provide definitive answers. 3I Atlas may continue to shroud itself in mystery, leaving us to oscillate between natural and artificial interpretations. But regardless of the outcome, this close flyby will stand as a milestone in astronomy, representing humanity's first opportunity to study in such detail a complex object from another star system. The process itself is making history, expanding the frontiers of human understanding. When December 19 arrives, as telescopes worldwide simultaneously turn toward that patch of sky, we are not merely observing a celestial body, we are attempting to answer an ancient question. Are we alone in the universe? And the answer may lie hidden within that distant speck of light, quietly awaiting our interpretation. As we systematically review all the anomalous features of 3I Atlas, a clear pattern gradually emerges. These anomalies are no longer isolated puzzles, but interconnected pieces of evidence. The first significant pattern is the discordance in its intrinsic physical properties. It simultaneously exhibits characteristics of both comets and asteroids, yet does not fully align with any known category. Low water content and a peculiar nickel-iron ratio make it resemble a metallic asteroid. Active jets and a dormant state, however, align it with comets. This contradictory combination is exceedingly rare among solar system bodies. The second pattern is the anomalous consistency in its dynamical behavior, from orbital parameters to rotational characteristics, from jet direction to non-gravitational acceleration. All these dynamical features exhibit an unnatural precision. They aligned perfectly with engineered optimization, rather than being products of natural random processes. The third critical pattern is the concentrated occurrence of multiple low-probability events. The probability of precisely crossing the ecliptic plane is approximately 0.2%. The probability of a retrograde orbit is approximately 1%. The probability of anomalous components is below 1%. The probability of anti-minus solar jets is extremely low. When these independent low-minus probability events occur simultaneously, their combined probability exceeds the realm of reasonable coincidence. The fourth pattern is intelligent traces in the time series, from the concealed timing of Pearl-Hannah to the precise arrangement of planetary flybies, and the unconventional correlation between activity levels and solar distance. These temporal characteristics reveal a strategic pattern, rather than a natural random process. Most crucially, these anomalies mutually corroborate each other. The rotation period precisely meets artificial gravity engineering requirements. The directional jets perfectly explain the rotation deviation. The anomalous components align with the propulsion system hypothesis. The non-gravitational acceleration is compatible with the camouflage strategy. This cross-disciplinary consistency of evidence holds immense scientific significance. When evidence from diverse fields, including orbital mechanics, materials science, and plasma physics, point to the same conclusion, the reliability of that conclusion is greatly enhanced. Pattern recognition tells us we are not dealing with an ordinary natural phenomenon, but with a highly complex system. This system either represents entirely new natural physics or technology beyond human comprehension. Throughout scientific history, when multiple anomalies cluster in a discernible pattern, it often heralds the arrival of a paradigm shift. The dawn of the Copernican revolution stemmed from recognizing anomalous patterns in planetary motion. Darwin's theory of evolution emerged from insights into biographic distribution patterns. For the 3I Atlas, these anomalous patterns may similarly guide us toward a new stage of understanding. Whatever the ultimate answer may be, the subject has already demonstrated that the universe is more complex and mysterious than we imagined. Each anomaly is a clue left by the cosmos. The patterns that connect these clues serve as the map guiding our journey. What we must do now is courageously follow this map, no matter where it leads us. The emergence of 3I Atlas is fundamentally reshaping how we perceive interstellar objects. Historically, we generally assumed interstellar visitors would be relatively simple celestial bodies, either rocky fragments like Oumuamua or frozen comets like Borisov, but the complexity and anomalous characteristics revealed by 3I Atlas compel us to rethink this fundamental assumption. It has first altered our detection strategies. Astronomers now recognize the need to establish more sensitive monitoring networks dedicated to capturing interstellar objects entering the inner solar system. Early detection is crucial. The sooner we discover them, the more time we have for detailed study. Existing sky-survey programs like the Vera C. Rubin Observatory are adjusting their observation strategies to enhance detection sensitivity. A significant shift has also occurred in research methodology, starting with the study of 3I Atlas. Scientists have developed a systematic checklist for identifying anomalous characteristics, including orbital analysis, composition determination, activity characteristics, and dynamical behavior. This methodology will be applied to all future interstellar object research, ensuring no potential anomalous signals are overlooked. For the field of extraterrestrial life search, 3I Atlas has brought revolutionary implications. Traditional LSETI programs primarily listen for radio signals across the cosmos, but 3I Atlas hints at another possibility. Physical probes may already exist within our solar system. This paradigm of searching for in situ extraterrestrial intelligence provides crucial complementation to traditional remote detection. Future interstellar object research will increasingly emphasize multi-messenger astronomy, integrating electromagnetic observations, gravitational wave detection, and even neutrino detection to construct comprehensive celestial profiles across multiple dimensions. Simultaneously, we will develop dedicated mission concepts to enable rapid response upon discovering the next anomalous interstellar object. The 3I Atlas also fosters interdisciplinary collaboration, where astrophysicists and material scientists jointly analyze anomalous compositions, orbital mechanics experts and aerospace engineers discuss their dynamic properties. Biologists This collaborative model of big science will become the standard for future research. Regarding technological advancement, the 3i Atlas inspires us to advance our space exploration capabilities. Should similar anomalous interstellar objects be discovered in the future, we aim to launch probes for close-range investigation. This requires developing rapid response launch capabilities, along with more advanced autonomous navigation and sampling technologies. Most significantly, 3i Atlas has reshaped our expectations. We now recognize interstellar objects may be far more complex than imagined. They may carry rich information about other stellar systems, and potentially even harbor traces of other civilizations. This paradigm shift will forever alter how we explore the cosmos. The 3i Atlas research process underscores the critical value of scientific transparency. From initial data delay controversies to subsequent open discussions, this case demonstrates the intricate ecosystem of modern scientific research. Science is no longer confined to laboratory work. It involves data sharing, public understanding, and international collaboration. The data delay incident during the government shutdown, though justified by administrative procedures, inflicted substantial harm on the scientific process. This lesson underscores the need to establish more flexible data release mechanisms, especially when confronting potentially significant discoveries. Scientific transparency extends beyond data sharing to encompass openness in the research process itself. In the 3i Atlas study, scientists promptly released preprints and publicly discussed preliminary findings. This openness accelerated scientific discovery and enabled the global scientific community to participate in this exciting exploration. For public education, the 3i Atlas serves as an exceptional teaching case. It demonstrates the entire scientific process, from identifying anomalies, proposing hypotheses, testing predictions, to refining theories. The public can intuitively grasp how science operates. Through this real-world example, science communicators face a critical challenge: to maintain scientific rigor while making complex knowledge accessible. For topics like the 3i Atlas, it's essential to convey its potential significance, while avoiding sensationalism and alarmist conclusions. Astronomy outreach in the social media era demands new strategies. Short videos, data visualization, interactive simulations. These tools help the public better grasp complex scientific concepts. Astronomers and science communicators are learning to wield these new instruments to make the mysteries of the cosmos more accessible. The 3i Atlas also underscores the importance of science education. When confronted with discoveries that may challenge established beliefs, a scientifically literate public can engage with and comprehend these discoveries more rationally, rather than succumbing to panic or blind skepticism. In this process, scientific institutions bear a special responsibility to balance research rigor with the public's right to know, while maintaining scientific credibility when communicating uncertainty. This demands the establishment of more robust science communication systems and the cultivation of more professional science communication teams. Ultimately, the story of the 3i Atlas teaches us that scientific exploration is a shared endeavor for all humanity. Regardless of the nature of this mysterious object, its study has enriched our knowledge, enhanced our capabilities, and deepened our awareness of humanity's shared destiny within the vast cosmos. When we gaze upon the stars, we seek not only answers, but also a better version of ourselves. This journey requires the participation and understanding of every individual, and therein lies the true significance of scientific transparency in public education.